Hi everyone, my name is Sierra Young. I'm an assistant professor and extension specialist in the Department of Biological and Agricultural Engineering at NC State, and my work focuses on robotics and automation in precision agriculture. So today I'm going to talk about some recent advances and ongoing work as it relates to machine learning and robotics for autonomous weeding. And I've chosen the application of autonomous weeding because it is such a persistent and important problem for nearly all agricultural production. And we've seen that this is likely going to be one of the first adoptions and applications of agricultural robotics on the farm. And so to first kind of frame this discussion, it's important, I think, to understand what makes a machine a robot. And so there's a difference between a machine that might be automated, we sometimes think of this case as in manufacturing, versus an intelligent system. There's many definitions for what a robot is, but conceptually we can think of it as a machine that is programmable by a computer that can execute tasks autonomously or automatically by itself. And so this is some machine that embodies an artificially intelligent agent. And so to highlight this, we can look at a RC remote controlled small drone and ask us the question of, is this a robot? And the answer is no, because this requires some input from a human to control it the entire time. But if we take that same system and put additional sensors on it, that gives it the ability to fly autonomously, detect and avoid obstacles, and perform some other actions by itself, now we can see that this starts to fit our definition a little more clearly of what a robot is. And within even the category of a robot, these systems can have different levels of autonomy. And this is a really nice chart that specifically focuses on autonomy for agricultural machines. And so we can see here in this first category where these vehicles may just have guidance between rows, and it goes all the way up to full autonomy where no human local supervision is necessary and everything is fully autonomous within the system itself. And so many available robots are not quite there yet, probably still in this first 2 to 3 categories, but ultimately that full autonomy, even supervised autonomy, is the goal. And to motivate why agricultural robotics are so important, especially in the context of weed control, we can look at this report that kind of forecasts weed science out to 2050, and looking at the steadily increasing trend of additional herbicide-resistant weeds, as well as the relatively stagnant trend of introducing new herbicide sites or modes of action to control weeds. And so looking at these trends, as well as the increasing efficiency in computational power, communication networking, and increase in our understanding of biological systems, these two trends together really set the stage nicely for introducing agricultural robotics, particularly for automating the weed control process. And just to take a look at some recent progress that has led to the development of commercially available sensors and systems for doing some form of autonomous weed removal. So most of the commercially available systems and sensors use computer vision approaches, and really what that means is that they're looking at shape and color of the weeds and using that information to detect what is crop and what is a weed, and also combining this information with the geometry of crops typically planted in rows. So some systems look to see where the row is, and everything that is identified as green within the row is a weed, such as the green weed seeker sensor. There are also some other technologies that use the shape or expected shape of some crops to identify crops and weeds. But ultimately, these technologies using computer vision are pretty mature, and they are developed in some autonomous, in quotes, cultivators. Why do I have autonomous in quotes? Is because these systems still need to be pulled by a tractor. So while they're not autonomous in their mobility, the implements on these machines do implement a sense, think, act approach where they act according to what the sensor is telling the machine to do. So this is one example of an autonomous mechanical cultivator developed for hoeing in vegetables. Most of these technologies were originally developed for vegetables, other high-value specialty crops, but we're also seeing a trend in kind of taking this technology and also developing it for row crops as well. This is the Garford in-row weeder, and this company has developed image analysis techniques to locate individual plants. And this weeder uses this technology in combination with tillage tools to mechanically remove weeds from between and within multiple crop rows. Now to look at what is happening now in both research and kind of startup companies developing some more automated systems for weed removal. So Blue River is probably something that comes to everyone's mind. This company has really been at the forefront of developing see and spray smart technologies that are a little bit more sophisticated. So this particular system uses both machine learning and computer vision, originally developed in cotton, to detect cotton plants and also individual weeds and make a decision about every single plant in the field. So if the plant is detected as a cotton plant versus a weed, that's how the machine then makes a precision spray decision. And so you can see that this system spans many more rows. It's more of a row crop, precision spray piece of equipment. But it definitely uses a little bit more sophisticated artificial intelligence for doing the plant weed identification. This is another smaller autonomous system that uses machine vision technologies in a little bit more of a controlled lighting environment. You can see those light pulses to detect weeds and apply a small, precise amount of chemical only to those weeds. This is a similar approach that is taken by Blue River's see and spray system, just in a smaller form factor. This is a smaller autonomous system developed by a Bosch company, Deep Field Robotics. And this system uses similar computer vision technology to detect crops and weeds and mechanically remove weeds using cutting tools instead of tillage tools. These systems are smaller and can also autonomously operate in a fleet, as shown here. And also, in addition to the development of these systems, we're also getting a lot better at detecting weeds. And not just detecting weeds versus crop, but also detecting between individual weed species. And this is due to an improvement in deep learning applications. And so to clarify the difference between artificial intelligence, machine learning, and deep learning, perhaps people use these terms interchangeably, but really deep learning is a subset of machine learning, which is a subset in this broad field of artificial intelligence, where in deep learning, the learning networks adapt and learn. So not only can they learn on their own, but they can also adapt to improve the model output. But to do this, a lot of data is required to train the model. And how much effort goes into training some of these machine learning models? Well, really data collection, data cleaning and labeling and augmentation. So everything that you see here that is red all goes into preparing these machine learning models. So they can take quite a bit of effort up front to deploy, but once they're developed, they can be extremely accurate. Just as an example, this was a data set and a deep learning model developed by a research group in Australia. And to train their deep learning model, they had manually labeled, which means in each image you identify the weed species and where that weed is within each image, over 17,500 images. And these images then went into training a deep learning model. But because they had such a robust training data set, they're seeing accuracies for detecting not only weeds versus crop, but also weed species at around 95%, which is at least what we'd want to see for any field system being implemented. So this is really exciting, and deep learning is opening up a lot of opportunities to do more precise weed identification. So what is coming perhaps in the farther future as it relates to autonomous weed removal agricultural robots? So as I mentioned previously, with all of this work around deep learning, we can take that information and then implement it on a system that has multiple modes of weed control on it. So for example, this is another system developed by a different research group at Australia, where they have their algorithm to detect between multiple weed species. And ultimately, depending on the information, they can then apply a specific amount of herbicide to the weed, or if that weed is detected as being perhaps herbicide resistant, implement a mechanical weed removal tool. And so this really enables site, field, crop, plant-specific weed management that I think is really exciting. And perhaps even farther in the future, we're seeing some of these conceptual or really early startup stage companies that are looking at developing fleets of robots. And so the benefit here is that you have a larger number of smaller systems that are more resilient and redundant to system failure. They can cover large areas, they can all operate simultaneously, and the cost of each of these smaller systems is of course much less than the cost of a single large piece of agricultural machinery. And to begin to wrap up, I just wanted to highlight that through the development of all these agricultural robots and technologies, they're really not going to be a silver bullet solve all problems as it relates to weed removal and weed management. They're really a tool in the toolbox that perhaps seeks to make weed removal more effective by perhaps enabling multiple forms of weed control, both mechanical and chemical, and also to make weed control and weed removal more economic by precisely applying chemical only to where it is needed. And so just to make that clear is that this is really part of a larger approach that's not going to replace everything that's currently being done, but really to enhance and improve weed management strategies. And to wrap up, I just want to highlight that despite all of this automation we see in the agricultural robotics, precision agriculture communities, that humans still matter. So I think it's important that these systems don't get developed with the goal of completely replacing the human in these operations. I think what we have in terms of knowledge, expertise, and experience is invaluable. And so really making sure that these systems are designed to enhance or augment what humans are good at, and then automate what perhaps humans don't need to spend all their time doing. And so this is kind of the framework that my own research seeks to implement when looking to develop technologies in the precision agriculture space. So with that, that's all I had for today. If you have any questions, please feel free to reach out to me via email. Otherwise, thank you for watching, and I hope you enjoyed this talk.